Force on a current carrying conductor in a magnetic field. This is our today's topic. In our last class, we have learned that an electric current flowing through a conductor produces a magnetic field. How can we find this magnetic field? Can you recollect how we find this magnetic field? Yes, if we place a compass near this current carrying wire, this compass will show deflection. And this magnetic compass is made up of magnet. And the field so produced exerts a force on a magnet placed in the surroundings of the conductor. Then only it can show deflection. That means the field so produced is exerting a force on a magnet. French scientist André Marie Ampere suggested that the magnet must also exert an equal and opposite force on the current carrying conductor. Can you recall Newton's third law, which you have studied in your 9th standard? That is, Newton's third law is for every action there is an equal and opposite reaction. This is the Newton's third law. Can we apply this Newton's third law here? Yes. Here current carrying conductor is producing a force on a magnet. Then the magnet will exert an equal and opposite force in a current carrying wire. Another way to understand this thing is that means we know that current carrying conductor is producing a magnetic field. This current carrying conductor is similar to a magnet. Then only it can produce a magnetic field. When this current carrying wire is kept near a magnetic needle, this is just like two magnets are kept near to each other. We know that when two magnets is kept near, it will attract or repel each other. So there will be a force between the current carrying wire and the magnet to repel or attract. Then only this repel or attraction or repulsion will take place. Behavior, that is, the current carrying conductor experiences a force when placed in a magnetic field was observed in 1821 by a scientist Michael Faraday. If a conductor is placed in a magnetic field and when you pass current in the wire, a force is exerted on the wire which makes the wire move, and when there is no current in the wire, there is no force. Another thing observed is maximum force is experienced when the current carrying conductor is placed perpendicular to the magnetic field. When the conductor is placed along the magnetic field, that is, when the conductor is placed parallel to the magnetic field, then the force on the conductor is 0. And if a current carrying conductor is placed at an angle to the magnetic field, it will experience a force. But to get the maximum force, the conductor should be placed perpendicular to the magnetic field. When a current carrying conductor is placed on a magnetic field, the magnitude of the force depends on three factors. When a current carrying conductor is placed on a magnetic field, the magnitude of the force depends on three factors. That is, force is directly proportional to the strength of the magnetic field. Magnetic field can be represented by the letter B. Next, F is directly proportional to current. That is, force is directly proportional to current I. And then F is directly proportional to length L, which is present in the magnetic field. By combining these three factors, F is directly proportional to BIL. We know that we can't apply a directly proportional in a numerical. So, to change directly proportional equation, we need to add a constant K. That is, F is equal to K into BIL. In SI unit, K is 1. Now, the formula becomes F is equal to BIL. It is easy to remember, that is, F is Bill. You can remember like this. If we rearrange the formula, we can find the SI unit of the magnetic field. That is, F is equal to BIL. We just converted B kept on one side and all the other things on other side. Then B is equal to F divided by IL. And the unit of force is Newton by, and the unit of I current is ampere, and the unit of the length is meter. So we can write it as the SI unit of magnetic field is Newton per ampere meter, and the name of this is Tesla, and it can be represented by the letter T. And another unit for the magnetic field is Weber per meter square. So we studied the factors affecting the magnitude of force. Now let's study the direction of force on the current carrying conductor when it is placed perpendicular to a magnetic field. We can easily find the direction of a force using a rule called Fleming's left hand rule. For Fleming's left hand rule, you must hold your yes, you can hold your hand like this, and that is for Fleming's left hand rule, hold your left hand like this with forefinger, that is pointing finger, center finger, this is center finger, this is pointing finger, and this is the thumb of your left hand at right angles to one another. It should be at a right angles to one another. It should be like this, and the forefinger represents the direction of magnetic field. Too easy to remember. Forefinger means your pointing finger, chund viral. That can be represented as field. F for forefinger, F for field, and the center finger. The center finger for current. C for center finger and C for current. Then this thumb represents force. And here also you can easily remember C for current, C for center finger. And the thumb represents the direction of force in the conductor. So let's see how can we use Fleming's left hand rule to find the direction of force on a current carrying conductor placed in a magnetic field. Let's start with the magnetic field. This is the magnetic field. Remember, the direction of the magnetic field is from north to south. This is the direction of the magnetic field. Here, a forefinger we are using, that is for representing magnetic field. So, forefinger is for magnetic field. So, hold the forefinger like this along the direction of magnetic field. Next, look at the direction of current. So, keeping the forefinger along the magnetic field, now point your center finger along the direction of current. You can see the current is in the downward direction. So, your center finger is pointing downwards. Now, then the thumb will automatically give you the direction of force. The thumb will automatically give you the direction of force on the wire. That may be like this. The force may be like this on the wire. As you can see, the direction of the force is outwards. You must keep your 3 fingers at 90-degree angles, and you must rotate your hands at the wrist in order to find the question that is given to you. So what are the things we study now? When a current carrying conductor is placed in a magnetic field, it experiences a force. And second thing is Fleming's left hand rule. Fleming's left hand rule is to find the direction of force. When magnetic field is given and the current is also given, we can find the direction of force using Fleming's left hand rule. So, while using this Fleming's left hand rule, you must keep your 3 fingers at 90-degree angles. Your left hand's 3 fingers at 90-degree angles, and you must rotate only your hands from at the wrist in order to find any question given to you. Devices that use current carrying conductors and magnetic fields include electric motor, electric generators, loudspeakers, microphones, and measuring instruments.